Okay, so you've given us a ton of stuff to go through today, and honestly, it's some pretty wild stuff.
Yeah.
Like we're talking about propulsion,
Propulsion.
but
Without,
without any moving parts, no engines, no propellers.
yeah.
Kind of feels like something straight out of Star Trek.
Yeah. Yeah. It definitely has that kind of futuristic vibe to it, right?
It does. But the thing is, based on all this stuff you've given me, this isn't just fantasy. This is like real science, and we're going to try to unpack that for everybody today. And
Yeah. And you've given me a really amazing collection of sources here.
Yeah.
You know, everything from like, what it actually is, what this idea even means, to the challenges and the research,
yeah,
how we even begin to develop this technology, what we could use it for.
yeah, what it would look like.
Yeah, there's even some like schematics and diagrams of
sure.
potential systems, and then even the materials that we might use.
So we've got a lot to cover today.
We do.
And I guess the place to start is, how do we even wrap our heads around the idea of, generating motion without any physical mechanics? I mean, it sounds kind of impossible.
Yeah, it really does defy our everyday experience, right? Yeah. I mean, we're so used to engines and wheels and propellers, things that physically push against something else to create motion.
Right. It's like action-reaction.
Exactly.
Yeah.
But here we're talking about something completely different. We're talking about tapping into these really fundamental forces of physics. Like quantum mechanics.
Quantum mechanics?
Electromagnetic fields, and then figuring out how to manipulate them with incredible precision. It's about engaging with the fabric of reality at a much deeper level.
Yeah, so let's talk about those core ideas. So we've got quantum tunneling, right? The idea that particles can pass through barriers that they shouldn't be able to.
Right, like going right through a wall.
Right, and then there's the Casimir effect, this weird force that comes from the vacuum itself.
Yeah, it's like the emptiness of space is actually pushing things around.
It's wild.
Yeah.
And then there's this whole idea of precisely controlling electromagnetic fields and like weaving them together to create motion.
Yeah. And to manage all of this complexity, we need AI. That's absolutely essential.
Right. AI is like the conductor of this whole orchestra.
Exactly. It's the brain behind the operation.
So we've got these really mind-bending concepts, but how do we go from those to actually moving something, a satellite, a car, a person, without any traditional mechanics? What are the big roadblocks here?
Yeah, that's the million-dollar question, right? There are some serious hurdles to overcome, and your sources do a good job of laying those out.
Okay, so give me the biggest challenge.
I would say energy efficiency is right up there.
Okay.
How do we generate enough thrust to move something significant without needing a ridiculous amount of energy?
Right, because with, an engine, you burn fuel and you get thrust.
Right.
You get motion.
Yeah, it's pretty straightforward.
This is like...
But here we're talking about these subtle quantum or electromagnetic interactions that are not as readily available.
Not so straightforward.
Right, so that's a huge
So like energy efficiency. So what's the next big hurdle?
Scalability is a big one.
Okay.
A lot of the effects we're interested in, like the Casimir force or quantum tunneling experiments, they work great in the lab at tiny scales.
Right, they're super tiny.
Yeah, but how do we scale that up to move something, even as big as a drone?
Right.
That's a massive leap.
Massive leap. So it's not just about proving it can work in principle, it's about making it work in the real world.
Exactly.
Okay, what else?
Well, controlling and stabilizing the movement is another huge challenge.
Because we don't have physical thrusters.
Yeah, we're basically talking about creating force fields or manipulating probabilities to get things to move, making sure that motion is accurate, stable, and predictable. That requires an insane level of control.
And that's where the AI comes in, right?
Exactly. AI is the key to making it all work in real time.
Okay, so we've got energy scalability control. And I'm guessing materials are another big issue.
Oh, absolutely.
Yeah.
We can't just use ordinary materials. We need to develop advanced nanomaterials that can handle and manipulate these quantum and electromagnetic forces at the atomic level.
Right, because we're talking about interacting with the universe at a scale we've never really done before.
Yeah, we're pushing the boundaries of material science, for sure.
Okay, so those are the big challenges. Now let's talk solutions.
All right, let's get to the fun stuff.
So your sources talk about this concept of quantum propulsion, which sounds amazing, but what does it actually mean to use quantum mechanics for movement?
So remember, quantum mechanics is all about the weird rules that govern the subatomic world.
Right.
So we have things like quantum tunneling, where a particle can pass through a barrier even though it doesn't have enough energy to do so.
Right, just like poof, gone.
Right, and superposition, where a particle can be in multiple states at the same time.
Okay, yeah, that's the one that always blows my mind.
Yeah, it's wild. So the idea with quantum propulsion is to somehow use these quantum behaviors to generate directed momentum.
So like tricking the universe into pushing something forward.
In a way, yeah. It's about exploiting the inherent fuzziness of the quantum world.
That's amazing. And then there's this concept of vacuum energy or zero-point energy.
Right, that's another piece of the puzzle.
So how does that fit into this quantum propulsion idea?
Well, even in a perfect vacuum, there's still a tiny amount of energy present due to quantum fluctuations in the electromagnetic field.
So like the vacuum isn't really empty.
Exactly. It's buzzing with energy. And the zero-point energy is everywhere.
Wow.
So the big idea, and this is still very theoretical, is that if we could tap into this energy and create an imbalance, maybe we could generate thrust.
So like pushing off of nothing?
Exactly. Pushing off the fabric of space itself. It's a pretty wild concept.
It is wild. But what's the current research focusing on in this area?
Well, there are two main areas of focus. The first is zero-point energy harvesting, which is all about developing materials that can actually extract usable energy from these vacuum fluctuations.
So like building a battery that runs on empty space.
Kind of, yeah. It's a long shot, but the potential payoff is huge.
Right, unlimited energy.
Right. And then the second area of focus is the quantum tunneling drive, which is looking at ways to use quantum tunneling as a basis for propulsion.
So like building a spaceship that can tunnel through space-time?
Well, not quite that dramatic, but it's about using quantum tunneling to generate a controlled and directed force.
Okay, so that's quantum propulsion. What about electromagnetic field propulsion? Does that use similar ideas?
It's different, but it's still about manipulating fundamental forces. So instead of quantum mechanics, we're talking about electromagnetism, which is a force we're more familiar with in our everyday lives.
Right.
So the basic idea here is to use electromagnetic waves emitted by specially designed materials to create thrust.
So instead of pushing something with a propeller,
Right.
we're pushing it with electromagnetic waves.
Exactly. It's like a super sophisticated version of how sunlight pushes on a solar sail.
But with a lot more control, right?
Yeah. We need incredibly precise control over these fields to make it work, and that's where AI comes in again.
Right.
AI would be essential for optimizing these field interactions in real time.
So it's like the AI is shaping and directing the electromagnetic fields to create the desired motion.
Exactly. It's like a conductor leading an orchestra of electromagnetic waves.
I like that analogy.
Yeah.
So what's the research focused on for this approach?
Two main things. The first is nano-engineered metamaterials. These are artificial materials with really unique electromagnetic properties.
So they're designed to interact with electromagnetic waves in specific ways.
Exactly. And they allow us to do things that are impossible with natural materials.
Okay. And the second area of focus?
Electromagnetic thrust arrays. These are basically arrays of tiny nanoscale thrusters that use electromagnetic fields to generate propulsion.
So we're talking about a lot of tiny thrusters working together.
Yeah. It's like having millions of microscopic hands pushing on the object.
Wow. And all of this controlled by AI.
All orchestrated by AI.
It's pretty mind-blowing. Okay, so we've covered quantum propulsion and electromagnetic field propulsion. What's next?
Well, there's another really interesting approach called Casimir-based propulsion.
The Casimir effect. Yeah, that one's always intrigued me. Can you remind us what it is again?
So the Casimir effect is this strange force that arises from the quantum vacuum.
Okay.
So remember how we talked about zero-point energy in the vacuum?
Yeah.
Well, when you put two uncharged parallel plates really close together in a vacuum, the range of quantum fluctuations between them is limited.
Okay.
And this creates a pressure difference.
A pressure difference in empty space.
Yeah, it's like the vacuum itself is pushing the plates together.
Wow.
And this force is tiny, but it's measurable.
So the idea is to use this force for propulsion.
Exactly.
Yeah.
By carefully designing these plates and controlling the gap between them, we can potentially generate a net thrust.
So we're literally harnessing the energy of empty space to move things.
It sounds crazy, but that's the basic idea.
What kind of research is happening in this area?
Well, they're working on Casimir thrusters, which are basically nanoscale devices that use the Casimir effect to generate controlled thrust.
So like little tiny engines powered by the vacuum.
In a way, yeah. And the other big area of research is material design.
Right, because you need really precise nanostructures to make this work.
Exactly. We need to create plates with the right geometry and the right spacing to exploit the Casimir effect effectively.
Okay, so we've got these three main approaches to non-mechanical propulsion, quantum electromagnetic and Casimir-based. But it seems like AI is crucial for all of them.
Yeah, AI is absolutely essential. It's not just a helpful tool. It's the brain that will make all of this work.
So it's more than just running simulations. It's actually controlling the propulsion system in real time.
Right. It's constantly monitoring the system, adjusting parameters, making sure everything is working optimally.
And what specific AI capabilities are needed for this?
Well, it needs to be able to adapt to changing conditions in real time.
Right.
Because these systems are incredibly complex and sensitive to tiny changes.
Yeah.
So the AI needs to constantly tweak things to maintain stability and efficiency.
And I imagine AI is also crucial for minimizing energy loss.
Absolutely. Energy efficiency is one of the biggest challenges with non-mechanical propulsion.
Right, we talked about that.
And AI can play a major role in optimizing the system to reduce energy waste.
So the AI is like a super efficient energy manager.
Exactly.
Yeah.
Making sure every bit of energy is used effectively.
Wow. And what about simulating these systems? I mean, they're incredibly complex. Can AI handle that?
Yeah, AI is essential for simulating these quantum and electromagnetic systems.
Right.
They're way too complex to model with traditional methods.
Right.
So AI allows us to test different designs and configurations virtually before we build anything physical.
It's like a virtual playground for testing out different ideas.
Exactly. And AI can help us explore a much wider range of possibilities than we could with physical experiments alone.
That makes sense. And are there any specific AI techniques being used for this?
Yeah, there are a couple of key ones. One is reinforcement learning, where the AI basically learns through trial and error.
So it's like training a dog.
Kind of, yeah. You reward the AI for good behavior and punish it for bad behavior. And eventually it learns how to optimize the system.
Interesting. And the other technique?
Predictive modeling. This is where the AI uses data to predict the outcome of different propulsion strategies.
So it's like having a crystal ball that can tell you how well a particular design will work.
Yeah, it helps us make better decisions about which designs to pursue.
Okay, so AI is clearly a game changer for non-mechanical propulsion. But it seems like nanotechnology is just as important.
Absolutely. We can't talk about this without talking about nanotech. It's the foundation that makes all of this possible.
Right, because we need to be able to build and manipulate things at the nanoscale.
Exactly. We need to create those tiny structures and materials that can interact with these fundamental forces.
So what specific nanotechnology applications are we talking about here?
Well, one is nanoarrays for field manipulation. These are basically arrays of tiny nanoscale structures that can generate and control the quantum or electromagnetic fields we need for propulsion.
So they're like the tiny antennas that send and receive the forces.
That's a good analogy. And another important area is self-healing materials.
Self-healing materials?
Yeah, materials that can repair themselves at the nanoscale.
Wow. Why is that important?
Well, these propulsion systems will be operating in some pretty extreme environments.
Right.
So they need to be able to withstand a lot of wear and tear.
And self-healing materials would allow them to last much longer.
Exactly. They could potentially repair any damage that occurs and keep the system running smoothly.
That's amazing. So we've talked about the big ideas, the challenges, the solutions, and the enabling technologies. Now, how do we actually make this happen? What's the plan?
Well, your sources outline a 4-phase development roadmap that lays out a path to making non-mechanical propulsion a reality.
Okay, so break it down for us.
So phase 1 is all about fundamental research.
Yeah.
This is where we really dig into the science and develop a deep understanding of how these systems work.
So lots of theoretical work and experiments.
Yeah, exactly. It's about building a solid foundation of knowledge.
And this phase would involve collaborations with universities and research institutions.
Absolutely. We need the best minds working together on this.
Okay, so phase 1 is all about laying the groundwork. What about phase 2?
Phase 2 is about prototyping and simulation.
So starting to build actual devices.
Right. We start fabricating the nano-engineered materials and the basic propulsion components.
And using simulations to test out different designs?
Exactly. We can use quantum computing to create highly accurate simulations of these systems.
So we can refine the designs in the virtual world before we build them in the real world.
Exactly. It saves a lot of time and money.
Right. Okay, so phase 2 is prototyping and simulation. What about phase 3?
Phase 3 is all about testing and validation.
So putting the prototypes through their paces.
Right. We take the devices we built in phase 2 and we test them rigorously in the lab.
So making sure they actually work as intended.
Exactly. And this is also where we start training the AI systems to control the propulsion.
So the AI is learning how to fly the ship, so to speak.
Yeah, exactly. It's learning how to optimize the system and achieve stable and efficient propulsion.
Okay, and then the final phase.
Phase 4 is scaling and production.
So this is where it gets real.
Yeah. Assuming the tests in phase 3 are successful, we start scaling up the production of these devices.
So going from small prototypes to larger, more practical systems?
Exactly. And this phase would also involve partnering with companies to explore real-world applications.
So like aerospace companies for satellite propulsion.
Yeah, exactly. And potentially even companies working on more futuristic transportation technology.
Like flying cars.
Well, maybe not flying cars just yet, but definitely new forms of transportation that we can't even imagine right now.
So this roadmap basically takes us from the drawing board to the real world.
Yeah. It's a long and challenging process, but the potential rewards are enormous.
Okay, so let's talk about those rewards. What are some of the potential applications for non-mechanical propulsion?
Well, the most obvious one is space exploration.
Right, because if you can move something without fuel...
You can go a lot farther.
Yeah, exactly. And you can do things that are impossible with traditional rockets.
Right. You could have satellites that stay in orbit indefinitely without needing refueling.
Or spacecraft that can travel to other stars.
Yeah, the possibilities are pretty mind-blowing.
And what about applications here on Earth?
Well, we could revolutionize transportation.
How so?
Imagine vehicles that levitate silently and effortlessly.
Like hoverboards?
More like hover cars or hover trains.
Wow, that would change everything.
Yeah, it would be a completely new way to get around.
So we're talking about a future where transportation is quieter, more efficient, and maybe even more fun.
Exactly.
Yeah.
It would be a pretty amazing transformation.
It would. And your sources also include some really cool conceptual schematics of these propulsion systems. Can you walk us through some of them?
Yeah, sure. So let's start with the quantum tunneling drive. The schematic for that one typically shows a particle injector.
Okay.
Which creates particles in a quantum superposition state.
Right. So the particles can be in multiple places at once.
Exactly. And then these particles encounter a potential energy barrier.
Like a wall.
Yeah. And normally they wouldn't be able to pass through. But here's where the AI comes in.
Okay.
The AI can actually manipulate the quantum probabilities to increase the likelihood that the particles will tunnel through the barrier.
So it's like the AI is nudging the particles through the wall.
Yeah. And this directed tunneling creates a net momentum which results in thrust.
So the AI is essentially controlling the flow of particles at the quantum level.
Exactly.
It's pretty incredible.
It is. What about the Casimir-based propulsion schematic? What does that one look like?
So that one typically shows two very closely spaced plates in a vacuum.
Right.
And the difference in vacuum energy between the plates creates the Casimir force, which pushes them together.
But how do you use that for propulsion?
Well, the trick is to design the plates in a way that creates an asymmetric force.
So the force is stronger on one side than the other.
Exactly. And the AI can control the shape and spacing of the plates to direct this force. So the AI is basically fine-tuning the Casimir effect to create thrust.
Exactly. It's a very delicate and precise operation.
Wow. And what about the electromagnetic thrust array schematic? What's that one like?
So that one typically shows an array of tiny nano emitters.
Okay.
And these emitters generate directed electromagnetic radiation.
So they're like tiny lasers.
Kinda, yeah. And the AI controls the pattern, frequency, and intensity of the radiation.
So the AI is basically shaping the electromagnetic field to create thrust.
Exactly. And the system would need an energy source to power the emitters.
Right.
Maybe a super efficient battery or even some kind of quantum energy harvesting in the future.
So these schematics really bring the concepts to life.
Yeah, they show us what these systems might actually look like.
And they make it seem a little less like science fiction.
Exactly. It's starting to feel more tangible.
Okay, so we've talked about the systems themselves, but what about the materials? We need some pretty amazing materials to make this all work, right?
Yeah, we do. We need materials that can interact with and manipulate these forces at the nanoscale.
So what kind of materials are we talking about?
We've got metamaterials, which are engineered materials with unique electromagnetic properties.
Okay.
They can do things that are impossible with natural materials.
Right.
Like bending light backwards.
Wow.
Yeah. And we've got graphene and other 2D materials which are incredibly thin and strong and have amazing electrical properties.
Right.
And we've got topological insulators which have conductive surfaces but are insulating in the interior.
Interesting. And what about superconductors? Don't they have some interesting properties too?
Yeah, superconductors have zero electrical resistance, which is pretty amazing. And they also exhibit the Meissner effect, where they expel magnetic fields.
So they're like magnetic fields?
In a way, yeah. And this makes them really useful for controlling magnetic fields.
Okay, and what other materials are we looking at?
We've got photonic crystals, which can control the flow of light.
Like traffic lights for photons?
Yeah, something like that.
Yeah.
And we've got rare earth materials, which have strong magnetic properties, and magnetic nanostructures, which can be used to create tiny magnets with very specific properties.
There's a pretty diverse range of materials.
Yeah, it is. And we're just scratching the surface of what's possible.
And the development of these materials is just as important as the development of the propulsion systems themselves.
Absolutely. It's all interconnected.
Okay, so to wrap things up, what's the ultimate goal here? What are we trying to achieve with non-mechanical propulsion?
The big picture goal is to completely revolutionize the way we think about and achieve motion.
It's not just about making things go faster or farther.
It's about breaking free from the limitations of traditional propulsion.
So it's a fundamental paradigm shift.
Exactly. It's about harnessing the most fundamental forces of the universe to move ourselves and our technology.
And this could have profound implications for everything from space exploration to transportation to our understanding of the universe itself.
Absolutely. It's a truly transformative technology with the potential to change the world as we know it.
And as we leave our listeners to ponder this incredible future, I have one final question for them. If we can truly master non-mechanical propulsion, how will that change our relationship with movement and our place in the cosmos?
Yeah, it's a big question to think about. How will our understanding of physics, technology, and even philosophy change if we can manipulate the very fabric of reality to move through space and time?
It's exciting to think about all the possibilities.
It is. It's a journey into the unknown. And who knows what we'll discover along the way.
Well, on that note, we'll have to leave it there for today.
Yeah.
But it's been an incredible deep dive into the world of non-mechanical propulsion, and we can't wait to see what the future holds.
Me neither. Thanks for having me.
Thanks for joining us.
It's been a pleasure.
And to all our listeners, thanks for tuning in to the Deep Dive. We'll see you next time.
See you.